And our first speaker is Navid Farahani from 3Scan. He's going to talk about how to connect macro-scale and nanoscale biology.
All right. Thanks for having me. This is my disclosure slide. Let me tell you a little bit about myself. I was initially a mechanical engineer, switched gears a little bit, went into medicine, did a 4-year combined residency in anatomic and clinical pathology. Then ended up down the street at UPMC where I did a fellowship in informatics and subsequently went to 3Scan where I'm currently a CMIO, non-paid scientific advisor to the Brain Preservation Foundation, and a paid consultant to Nectome. I have no formal degree or training in computer science, so if you ask me anything too difficult, I might relay you back to some of my colleagues. And I altered the content of this presentation, given yesterday's excellent talks, and I knew I was going to follow the Allen folks. And like other people in this room, my goal is to try and recruit some of you guys to come help us out. Most of the people I work with at these 3 organizations are MIT alumni, so CMU is poorly represented. I want to change that. So the motivation, as again, the previous speakers have already kind of shown you, biology is multiscalar. So down here we're at the nanoscale, and as we go higher and higher up, we go up to the meso and the macro scale. And beyond that, if we just hone in on one component here, the cells, for example, we find that they're massively complex. While we start with a single omni or totipotent stem cell that sort of turns into these 3 germ cell layers that then give rise to the trillions of cells that make up a single organism. The other motivation here is this is, I'm a board certified pathologist. This is our current workflow. So when I get organs, I have to cut them, I have to gross them into smaller, more manageable parts, and then we have to sort of run them through this very destructive process of prepping the tissue such that we can actually do a single sort of analysis. And the limitations herein are it's time consuming, it's destructive, and seeing as how we get a single 2-dimensional view of an inherently 3-dimensional organ, we have numerous sampling errors. And so this is kind of what it looks like. This is a cervical biopsy, and on the left we have sort of the normal epithelium, and as we sort of go along this direction, we see that there's some abnormalities that start to arise, and this is evidence of cervical intraepithelial neoplasia. And some of you might say, well, you sufficiently diagnosed this tumor, right? So you're doing pretty good, even with that very limited 2D view. These are some of my colleagues up at University of Washington who are doing some really cool work using light sheet fluorescent microscopy. And so this is a prostate core biopsy you see here. And pathologists are notorious for not even agreeing with themselves, let alone other pathologists. And so you see here they're grading as they go further down the needle core biopsy. And it sort of changes as they're going down from a 3.3 to a 3.4. This is the grading schema for prostate carcinoma. And the difference herein results in conservative treatment versus a radical resection. And so you know, there's a high degree of intra and inter-observer variability that can certainly be improved by actually giving people more information. I'm going to switch gears a little bit now. So our company was contacted several months ago by this large pharma organization, United Therapeutics, who has a very ambitious goal of wanting to print lungs for organ transplant. There's a limited supply of lungs, and lung cancer happens to be the most common malignancy for both males and females. And so they reached out to us and said, do you have a blueprint of lung tissue? Because we want to plug that into a 3D printer and use collagen to print the extracellular matrix. And I'm going to show you how we went about deriving this. This is kind of what we do at our company, which is actually very much inspired by the Allen Institute. We build these robotic platforms that we call the knife edge scanning microscope. And what it does, it sort of combines the sectioning and imaging into a single step. We currently have 9 robots. We're hoping to have 12 by the end of this year. And so we generate both lots of sections and lots of data. And we're trying to image 100% of the sample itself so that we can spatially index across whole tissue blocks. This is just a GIF showing you how that technology works. Again, simultaneous sectioning and imaging. We have a diamond blade here that's about 5 millimeters wide. We take our images or the tissue off in strips, and then we stitch those strips together. And again, this is kind of how our workflow goes. We have to switch things up a little bit, which makes things a little bit difficult. And we have to do whole block staining before we do our sectioning and imaging. And then we get the raw imaging. We clean it. We generate masks after segmentation. We then splay those masks out into contours, and then we stitch those contours into a mesh. And then we plug that into a printer to get our printed model. And so, again, these folks that approached us, they wanted not only an anatomical model on the sort of macro level, but they also want us to bridge that with things that are lower down at the micron and nanoscale. I'll show you we're at the micron level now, but so to show them the sort of larger scale anatomy, we took this is data from the Visible Human Project, NIH funded project in the late 80s, where they took 2 human cadavers, male and a female. They embedded them in large blocks of ice, and then they had a big diamond blade, and they cryo-sectioned them into 1 millimeter thick sections, and then they took photographs. It's really cool, but it's a very manageable 2048 by 1216 pixels. Anyways, we stitched that together into a 2D image stack, and then we went and had myself sort of segment the airways and the pulmonary vasculature. And what we eventually got was a 3D model of the airways, and this was very interesting for me because I'd learned medicine by looking at a bunch of anatomical textbooks, and when we actually segmented it, this matched up exactly to the images I had seen in those textbooks. And then we began splitting things up, so here we have the pulmonary veins, pulmonary arteries, and then we sort of combined them into our model that was eventually fed into the printer. Actually, let me take that back. So this is when we actually went and took subsequent sections from each one of those generations, and we fed them into our Kesem robots. So we sort of went through the same process. Our images are a magnitude larger, and this was actually 4 times down compressed. We do image segmentation and annotation. In this case, it was sort of automatically generated using thresholding. And then we do our 3D reconstruction. And we have now our sort of 3D model of the cartilage and bronchial wall. And then we took our previous model from the larger anatomical imagery, and we sort of created a skeleton, a spline, and then we took our data and we ran it along that spline. And so here you have a sort of hybrid model that combines these two, and it looks very Geiger-esque because, of course, your trachea doesn't look like that, and neither do the lower airways and whatnot. Anyhow, as we were doing this, we started to notice that many structures in biology are built from smaller and more simple things, much like fractal algorithms that generate more and more complex things. So as we began to accumulate terabytes of our lung imagery, we decided to begin creating mathematical descriptions of these structures. And eventually what we got were these subsegments. So in this case, we have a trachea, a tracheal ring, and we're sort of playing with configurations of the capillary mesh that surrounds it, and then we're slotting in the trachealis muscle and now the bronchial wall. We take that and we build larger segments. So in this case, we're showing you how we were able to generate a whole trachea, and we're able to rapidly sort of iterate on the various factors therein. And then we can take that and build it out further, and we get our tissue or organ level model. The reason why we sort of head in this direction is because we started to realize that our colleagues at 3DS that were doing the bioprinting, they really wanted to be able to rapidly sort of iterate on the models that we were giving them. It wasn't fitting in the proper print volume, and furthermore, the folks at UT really wanted us to give them something that would enable them to customize these prints. Maybe one day you don't want a pair of your own lungs, you want Usain Bolt's lungs or somebody else. This is just showing you what our robots see, and before I play this data set, I just want to sort of orient you. So this is giving you some metadata related to the sample. It's a human lung. We stained it with a Giemsa, and we sectioned it about 5 micron thickness. This is showing you the stride, so we're jumping every 20 sections. This is showing you how much we had to compress it to fit it on the screen. This is showing you the average size per one face, one section, And at the end, you'll see the accumulated data size for the tissue that's been cropped to the region. And this is what it looks like. So in dark purple here, these are cartilage rings. We just saw a big lymph node. Here's a big vessel. This is the inside of the airway, another lymph node. And so it ends up being about 80 terabytes for a single. This was the transition from your trachea to your mainstem bronchi. And this is going to be my remaining question slide. The challenges we're facing mostly relate to being able to store and move these massive data sets around, being able to enable folks like myself to annotate and segment them in a meaningful and sort of easy fashion. That's still a challenge for us. We're looking to partner with crowdsourcing websites that enable us to shove data into them and have other people help us out. But of course, they can only fit images that are 2 or 4K large. And these are all the folks that I work with who help me out. Again, we're actively recruiting. And if you have any questions, feel free to email me.
Are there any questions? OK. Let's thank our speaker again.